In the name of our Lord, the Beneficent, the Merciful, in part 1 of our Maxewell stress tensor topic, we learned about a particular vector identity which we are going now to use in this topic, in the main topic. We also learned about tensors. We are going to use that knowledge also here in this main topic. To begin with, imagine a particular region of space. Say suppose this is a particular region of space bounded by a closed surface S. The region has within it electric and magnetic fields. These fields may be due to an electromagnetic wave passing by, or these may be due to some other sources, current and these charges. And these electric and magnetic fields, they act on charged particles. Here are charged particles. These dots are charged particles. Suppose there is a charged particle Q. So what is the net force? Electromagnetic force, I mean force due to electric field and magnetic field on that charged particle. That is simply Lorentz force. That force is equal to force on charged particle Q. That is simply equal to QE plus, that is electric part of the force, Q V cross B, magnetic part of the force. This is force on a charged particle Q. Now, force on a, if we imagine this volume to be divided into small volume elements, each volume element, let us designate that volume element by d tau. Tau because we are using V for velocity. Now, if you have tau, d tau volume, and if charge density is rho, then charge within this small volume will be rho dt, d tau. dq will be equal to rho d tau. Force on this small amount of charge will be rho d tau from this rho d tau plus into E rho d tau into E V cross B. This is force on this small amount of charge, that is dq. Now total force if we denote that by F, that will be volume integral of rho d tau. We can take common, we have, or we can write it rho E plus rho V cross B, and let us take d tau common. Now rho V, you can easily recognize this. This is current density J is equal to rho V. Substituting that there, then total force on these charges in the region, in the volume, is given by F is equal to rho E plus J cross B into d tau. Now, what is force per unit volume? This is force per unit volume. This force per unit volume acting, you have simply to divide force by volume, and you can transfer this to this total volume here, and you have force per unit volume equal to rho E plus J cross V. You have now force here. This is our starting equation. Force per unit volume acting on the charges. Now, what we are going to do, our first task is to replace this rho and G from the equation first, to eliminate them. And in their place, we want only fields. Here, no rho, no G. Now, how to do it? We can use, for example, for eliminating this, we can use Gauss's law. which tells us that del dot E is equal to rho by epsilon naught. So if you want rho, it is rho is equal to epsilon naught del dot E. Okay. Having done this, you now have J. J can be obtained from value of J can be obtained in terms of fields. It can be obtained from this Maxwell's fourth equation, that is, curl of magnetic field is equal to mu naught J plus mu naught epsilon naught del E by del T. This is Maxwell's fourth equation. Now from this, you can get value of J. You have therefore mu naught J is equal to del cross B minus mu naught epsilon naught del E by del T. Now we want only J, so you can transpose this mu naught to this side. You have J equal to 1 by mu naught del cross B. This mu naught will cancel with this mu naught. You will be left with epsilon naught del E by del T. Now after this, we are now both replaced both. Now we have to replace. Now we have got value of both this rho as well as J. Substituting these in this equation first, we get F is equal to in place of rho, you have epsilon naught del dot E plus J cross B. Now J is this. Please remember, you have J cross B. The problem is that when you substitute J here, you forget about this B. And the whole thing then goes wrong. So be careful about this. We don't forget about this B. So you have J, in place of J, you have 1 by mu naught del cross B. Cover this up with this square bracket and minus epsilon naught del E by del T, and then cross B. Please, once more I stress this point. Please don't forget this. Cross B. Now, next, when you take cross product of these with this, F is equal to, therefore F is equal to epsilon naught del cross E plus, now cross 1 by mu naught del cross B minus mu naught del E by del T cross B. Two changes that I will make here. One is, I will put this in this form, B cross del cross B. That means A cross B, instead of A cross B, I will write B cross A. And I can do that, but with a negative sign. I have to change the sign then. And therefore, I will do F is equal to epsilon naught del cross E minus 1 by mu naught B cross del cross B. Why I have done this? Because I already know. In part first, we learned about an identity, vector identity. It was E cross del cross E, and we know now its value from part first. Now, similarly, you have the same thing applies to magnetic field. So what I have done, I have brought it in a form where its value is known to me. I will later on use that value, and I have now minus epsilon naught one more thing, that is not yet, del E by del T, del E by del T cross B. Now I want one more thing, that is I want a term like this, E cross B. Why? Because such a term would represent Poynting vector S. 1 by mu naught E cross B is equal to, that is equal to E cross B, that is equal to Poynting vector S. So such a term, that means I want such a term in this expression. But how can I do that? How can I get such a term? Not difficult. It is easy, quite easy. How? See, del by del T E cross B. This tells me that I should look for this. I should look for this del by del T E cross B. U product rule. This is equal to del E by del T cross B plus E cross del B by del T. Now this term, there you have del B by del T, and value of del B by del T can be got by Faraday's law. From Faraday's law, you know Faraday's law tells us that curl of electric field is equal to minus del B by del T, rate of change of magnetic field. Now it simply means that electric field is a changing electric field is associated with a magnetic field. Now, sorry, a changing magnetic field is associated with an electric field. Now you have substituting this, using this Faraday's law there, our expression, this product expression becomes, cross product expression becomes E cross B is equal to del E by del T cross B minus, because of this minus dV by dt is minus del E cross del cross B del cross E. You see, you have got that vector identity, that electric field vector identity. Now, okay, substituting value of this into above equation here in its place, I will write F is equal to epsilon naught del dot E, epsilon naught del dot E. Then I have minus 1 by mu naught B cross del cross B cross del cross B cross del cross B. Okay, then I have B cross del cross B, that's okay, but then minus this. Now from this I will get plus this. If I want minus this, without any confusion, this will be minus, this will be plus, and when you transfer this to that side, this will become minus there. So both of these terms will become minus there. So you have minus del E by del T cross B equal to minus, in this place you have to write minus del by del T E cross B, and then minus E cross, I will write it here, minus E cross del cross E. Now looking at this expression, you see there is some symmetry. This term is for magnetic field, this term is for electric field. There must be some mu naught, is it? Yes, it was mu naught del E cross by del T. I'm sorry, mu naught del E cross by del T. Mu naught mu naught, and you will have to supply mu naught here, mu naught, there too, mu naught. So you have this situation now. One thing that must be perturbing you throughout perhaps, that is this mu naught epsilon naught. If mu naught is in C, it appears with its magnetic field, it appears in denominator, this appears in numerator. The reason is that these are basically mu and epsilon, they are basically response of media to electric and magnetic fields. Now that means simply that if you have an electric force, electric charge, this is an electric charge Q1, this is another electric charge Q2, and there is medium between them. The force between them depends upon charge, product of charges, depends upon inversely square of distance, and it also depends on the nature of the medium. Now the interesting thing is that all material media reduce this force. That means this force is lessened in presence of matter. Different material media reduce it differently by different amounts, but all of them reduce it. That means material media have force reducing capability, and this force reducing capability is expressed by epsilon. So epsilon is basically force reducing capability, and it appears here. The greater the force reducing capability of a medium, smaller will be the electrostatic force there. Now take the case of magnetism. It is north pole, north pole. Suppose we had poles like charges, point poles. Suppose you can approximate them by taking very long magnets. Okay. Anyhow, the force between them, magnetic force, is roughly proportional to product of the strengths, inversely proportional to square of the distance, and inversely proportional. Now, if you place different material media between these two poles, these material media increase, most of them increase magnetic force instead of decreasing. They increase. For example, if you place a sheet of iron between them, magnetic force will increase by a very large factor. Almost all media except diamagnetic media, usually diamagnetism is masked by stronger paramagnetism and ferromagnetism. I will not say that all the media increases, but most of the media increases. So instead of defining a property that which means force reducing capability, we define here a property which means force enhancing capability. Force enhancing capability. Greater mu means if a medium has greater mu, it means greater magnetic force. So they begin their journey by this. One starts in the denominator, the other starts in the numerator. That is the cause, that is the basic reason of this. So after that, let us go back to our main topic. So you have now this situation. Okay, there is one perturbing thing, irritating, that irritates some of us. That is, there is an additional term, this term, epsilon naught del dot E for electric field, whereas there is no such term for magnetic field. As far as this term is concerned, two things about this term. Number one, it is shear term, shared by electric and magnet. Number two, we won't be changing it further. It will serve our purpose ahead. It will be important for us. Now, this term, we will keep it with us. It will describe this Poynting vector. Okay, rate of change of that. In fact, can we have a term similar to this for magnetic field? Yes, we can have. Now, I'm sorry, I have again committed an error here. It is not del dot E. It is del dot E into E. How? You can see it. Mistake has been commented here. Here itself. You have E and you have rho. You have to substitute in place of rho. You have to substitute epsilon naught del dot E, epsilon naught del dot E. But you have not to forget this E, and this is what I have done. I'm sorry for that, and I will separate here and again here, again here, again here, here again. Okay, now it is now correct. Now can I have a term of this type in for magnetic field? Yes, I can have. How? Because see, del dot B, divergence of magnetic field is always 0. Who told me this is 0? Because it simply means divergence means flux per unit volume. Magnetic flux through any closed surface is 0 because magnetic monopoles do not exist. This is in fact Maxwell's second equation or Gauss law for magnetism. Okay, then it will not cost us anything if I add this somewhere. So what my next step will be, I will group this in electric and magnetic terms. I will write epsilon naught del dot E into E. Then another electric term is minus epsilon naught E cross del cross E. Now magnetic term minus 1 by mu naught B cross del. Well, I should first of all I should do this thing. Okay. Now I should first write a term similar to this, that is del dot B into B, then this term minus 1 by mu naught B cross del cross B cross del cross B, and lastly minus epsilon naught E cross del cross E. Now it is better to have a check on this. For the sake of symmetry between electric and magnetic terms, the sign of del dot B, we should choose sign of del dot B positive instead of negative, because sign of del dot E is already positive. Since the sign is positive, so sign of del dot B should also be taken as positive. Therefore, we can write F as epsilon naught del dot E cross E del dot E, del dot E, not cross E into E. It's better to rub it and then write it afresh. You have epsilon naught del dot E into E minus E cross del cross E and minus 1 by mu naught as you have then plus 1 by mu naught, that is del dot B into B minus, which the original, this minus is the original sign of B cross del cross B. Okay. Minus lastly minus epsilon naught del E cross B by del t. Okay. We now use our vector identity. E cross, E cross del cross E is equal to del cross E is equal to 1 by 2 del E square plus minus it is minus E dot del into E. Similarly for the magnetic term, therefore F can be written as epsilon naught del dot E into E minus. Now here E cross del cross E. In that place you have minus 1 by 2 del E square plus E dot del into E. This plus is due to this minus. That is okay. Similarly for this term, plus 1 by epsilon naught you have inside del dot B into B, and then you have similarly minus 1 by 2 because B cross del cross B, minus 1 by 2 B square plus B dot del into B minus A epsilon naught del by del t E cross B. Now this whole thing looks terribly frightening, and by an ingenious technique, if I tell you that we can write this whole thing simply as F is equal to del dot t minus epsilon naught del by del t S mu naught S divided by you have as that is divided by mu naught E cross B is equal to mu naught. It is okay, mu naught, because E cross B divided by mu is equal to S. So E cross B is mu S. Okay. Now if I say that, I can express this whole mathematics by a simple term like this. Naturally, you will be excited to know how. The question is how can we do that? For that matter, what we do here is we define a tensor, second order tensor, Tij. We define it as, and you will ask question definitely, why do we define it as you write it, as you say? Why do we? I will not. We define Tij as equal to epsilon naught Ei Ej minus 1 by 2 chronicle delta Ij E squared plus 1 by mu naught Ei Bj minus 1 by 2 del Ij E squared. Now a few points about this. Number one, Tij is a second order tensor. That means it is these elements are Txx. Now start with this x, give x value to this I, xxy, x value to y, j, then txy, txz. Next we have tyx, tyy, tyz, and then we have tzx, T Z Y T Z Z. So these are the elements of this Tij. This tensor is a second rank tensor, second order, because it has two indices. Now its components are 9 components. Now as far as Txx is concerned, if we define it like this, like by this equation, then Txx will be, for getting value of Txx, you have to put both this x, then you will get epsilon naught Ex, that is x square minus 1 by 2. And you know about Kronecker delta. You know Kronecker delta is equal to 1 if I is equal to j. If I is not equal to j, it is 0. Since I is equal to j here, hence it is 1. So you get e square plus 1 by mu naught ey square ex square minus 1 by 2 b square. Now this is just one element. You imagine this element here. Then you have similarly txy. In txy, you have to in txy, you don't have these term and this term, because since it is txy, x is not equal to y. This is 0. This is 0. No terms involving e square. Then you have only this exey epsilon naught exey then plus 1 by mu naught e bx by. Similarly for other these elements of the tensor. We don't need to expand it. We don't need to find values of these elements. What we need is to feel it. Feel what we are talking about. It's a tensor, that means, and that too of second order. That means it is like a matrix. It's a matrix, and like matrix, it has and this matrix has 9 elements. Now we want to define something for this tensor. We already know, since we in part first, we have some idea of what a tensor is. Now we want dot product of this tensor with, say, I want del dot t. Now if you talk about dot product between two vectors, that is a scalar. No doubt about that. A is equal to, say, ax x cap. I'm not writing I cap because I'm using I here as indices. Ay j cap, y cap, and then az. K is z cap, then b is equal to a x bx x cap, by y cap, bz z cap. And when you take dot product, a dot b is equal to ax bx ay by, az bz az. The important thing is that this dot product is a scalar. That means it does not need any index. In number of indices that it needs, that is equal to 0, or equal to 0. It doesn't need an index. This needs one index, it is a vector. This needs another one index, it's a vector. But the dot product needs no index. That is, it is 0. Its rank is 0. This means that dot product reduces the order, or what some people call as rank. Okay. Now you have, with this thing, let us go to this. When you have dot product between a vector and a tensor, again, it reduces the rank. Now, what is the rank of tensor? Order of tensor, that's 2. If you now dot product it with this vector, you will get a vector. Instead of tensor, you will get a vector. And that means its rank will be reduced. You can yourself check it as we proceed. Let us check it along with that procedure. So we have del dot t. Now we want to calculate del dot t, and this del dot t, it is in fact it is jth component that comes out to be that complex expression for which we have introduced this tensor. Now, how to calculate this del dot G? In order to, I want to remind you one thing from my previous previous part 1 discussion. This polarization along x-axis is equal to alpha ex ey. I have not decided yet the subscripts of these, indices of these, but one thing that I am writing, that is x polarization can be due to x electric field, y electric field, z electric field, because polarization depends upon direction. Hence, a particular polarization in any direction can be due to a combination of x field, y field, z field. Now, as far as this is concerned, this constant is concerned, this constant, what we show, how do we show this constant? We show it x here. The first shows the component. Whose component it is? It is x component. Which component it is? Sorry, it is x component. Okay, x component of polarization. Second shows due to what? Due to which electric field? Due to x electric field. Then you have x component due to y electric field, x component due to z electric field. Point to be noted is that as you go along this sum, you are changing one variable, that is x, y, this second variable, second index. If I write tji, then you are changing I variable, you are giving values to I variable, and you are maintaining one variable same, that is the first index, x, and that is equal to this. That means we can write the jth component, or similar, it's simply jth component of this polarization is equal to alpha jx ex plus alpha jy ey plus alpha jz ez. Okay, now we can write this compactly as pj is equal to summation alpha ji, writing I for this second, right? I for this I index, so we have ei and then ei. Now you have sum over I. There are two indices here. One is j, another is I. You have to sum over I, not over j. You can see you are summing over I, the second index. In fact, sum is always taken over the repeated index. Which index repeats here? That's I. And you need not, as per Einstein's notation, you can write it simply as ji ei, where the repeating this index itself means that there is sum being taken over I. Let us now examine dot product of del and our tensor. It is jth component. In order to have a feel of what dot product is, how dot product is defined between a vector and a tensor, you just have simply to recall definition of dot product in case of two vectors. When you dot two vectors, you get a scalar. Scalar is known to be a tensor of rank 0, order 0, and a vector has order 1 because it needs one subscript, order 1. It means that dot product reduces the rank or order of the tensor. The starting tensors, they have each of them has an order of 1, and the resulting tensor has an order 0. This rank contraction is an important thing in tensor analysis, but we did not pursue it further. We don't need it much. Anyhow, what about this? How do we look at this? In the same manner in which you look at the dot product between these two. Say, for example, you just want this del dot t. Now you have del component, you write components of del, say del x, del y, del by del x, del by del y, del by del z, and then dot the dot product is same here as matrix product. You have txx components of this txx, txy, txz, tyx, tyy, tyz, and then tzx, tzy, tzz, tzz. Okay, then when you take this dot product, you are actually dot product is scalar multiplication. This goes with this. For example, you will get del by del x, txx, then del by del y, t yx, then del by del z, t zx, and so on. This will be the first term. Second term will be this into this. That will be here. Third term will be this into this. That will come here. Now the interesting thing is that the resulting entity is a vector because it has only three these components. There are only three entries, 1, 2, and 3. Thus rank reduction does occur. Number one. Number two, second thing is this will be the x component of that. So it will be del dot t x component. X component of del dot t will be this much. Now in this x component, what do you find? You find you have del by del x, tx y, txx plus del by del y, tyx plus del by del z, tzx. You can similarly think of other components. You have now x component. You have x here, y here, z here. Now you have here x, y, x, z, x. This and this, they are similar. This and this, they are similar. This and this, and this contains x, this contains x, this contains that component. If you are speaking about x component, x will remain, this x will, the x index will remain constant on this side. That means you have x here, del x, del this is your x actually, and this x is changing. This x is here x, here it is y, here it is z. You can call this, for example, you can say you call this ix. Similarly, you can call this del instead of del x, you can add del xi, where you let the I to be 1, 2, 3, or x, y, z, and take sum of that. This means simply it is del by del x, that is this, t xx. Then del by del y is t yx. Del by del z, we don't write usually, we don't write here del by del I. We don't write like that. We write usually x and write xi. Xi has the value x, y, z, or better, there is another way you can write it, Einstein's way, that is, you need not write this at all. You simply write it del I t I x. Even this is dropped, and this simply means del I t I x means exactly this. You are taking this as del x component, x differentiating with respect to x component of this, of course, x component of this, not of the and this dot product, del x t ix. So what do you observe? You observe that if you have x component written here, you have that x here and here. Not x is not here, sorry. X, it is I and you have to take sum over this I. You have to take this exactly del x t x x plus del, now give it y value, del y t y x plus del z t y z y x, sorry, zx, sorry, zx. So this, therefore we can write del dot t jth component is equal to, some people put the double arrow here, but that's not must. Del dot t is jth component, that is del I t ij, and as I told you, this simply means that you have to sum over I, that is you have to give values del x t xj, del y, giving value y to it, t yj plus del z t zj. As you see, for the jth component, j remains constant. And this del simply means del by del x. So in order to evaluate this, we have to substitute value of tij here. And when you do that, del dot t jth component is equal to del I. Now the value of tij, that, as you know, that is equal to eij minus 1 by 2 Kronecker delta ij e square. Then you have another term, that is this magnetic term, plus 1 by mu naught bij minus 1 by 2 del ij b square. Now in order to evaluate this, let us first give a number. Let it be equation third. We will evaluate it term by term so that you don't feel any difficulty. Let us take the first term. I will not take this epsilon naught, it is there, it's a constant. So I will simply take del I ej. Now this is a differential operator and it is differentiating this product. So we will first of all use our product rule, that is del I ei into ej plus ei into del I ej. Okay. This is our product rule. Now in order to evaluate the first term, this is the first term. This term, if you can look at it clearly, then this term you will recognize easily that it is del dot E. How? Let me show it. How it is del dot E. We have not written the second term, and please don't forget that. Let us first go to this. Now when you evaluate del dot E, for a moment you let me use I, j, k for these basis vectors, rectangular basis vectors. So I will write here del expression of del I del by del x plus j del by del y. This ij is not that ij here. Those are indices. Since I am not going to use this permanently, so there will be no confusion at all. We will rub it off just after we complete it, but it will make our understanding easier. Del by del y plus k del by del z dot e I ex j ey plus k ez, and see what it is. This is simply, this goes with this, I with I, that is del by del x ex plus del by del y, this with this ey, plus del by del z ez. As you see, we write, instead of del by del x, we simply write del ex del, now 1 minute, that is del ex by del x, del by del y. Now we will simply write it as del x ex, del y ey, del z ez, and that this is simply del dot e, okay, and this can be written as del I ei, where I means here x, here means y, here it means z. Hope that this is clear. I think it is clear to you. That is now here you can understand it in another way. You can write here, for example, in place of this you can write del x ex, del y ey, del z ez. You are summing over I, del z ez, and then this whole thing is simply this, and that is del dot e. Okay, let me rub this off in order to avoid confusions. We will go back to our E and to our I and J indices. Del, it is del I, Ej, and it is Ei here. By product rule you can check it. This is del Ei, Ej here, then Ei here, and then differentiation of Ej. Now we have finished the first part. We saw it is this. What about the second part, Ei? Well, we have to sum over Ei. Summing over Ei. That is, we have to write. Keeping it there, we have to write. Let us take it here. Ei, del I, Ej. Separately, we have to write it as Ex del x Ej. J is constant. Then Ey del y Ej. Del z Ez del z Ej. We are taking this as constant, J as constant, and summing over this K. Summing over this, J, Ei. And now what this is, this expression Ex, we can write it for your convenience. We can write it as Ex del by del x Ej, then Ey del by del y Ej, then Ez del by del z Ej. This, if you recognize it, you can easily recognize it. This is simply E dot del. With taking J out, E dot del J. Ej. How you can check it? Let us go to this again in rectangular coordinates. Ex plus J Ey plus K Ez dot you have I d by dx, J d by dy plus K d by dz. Okay, this is equal to, now I with I, Ex del by del x, okay, plus Ey del by del y, del by del y, plus Ez del by del z. Now check it here. Ex del by del x, Ey del by del y, Ez del by del. That is, I think now it is quite clear. Okay. Having shown this, we are now left with one more term. That is minus 1 by 2 del ij e square. Minus 1 by 2. So I have to write minus 1 by 2 del this is del chronicle delta E square chronicle delta E square. You can see it yourself. You have now you know del ij. Del ij is equal to 1 if I is equal to j and is equal to 0 if I is not equal to j. That means it selects only that value of I which is equal to j. If that is the case, then it means, first of all, let us do one thing. Let us take all the values of this. Say we write it minus 1 by 2. This okay, I have now written it. There was no need to carry this minus 1 by 2 along with us. Then along with this, you have del, then you have del ij. Now let us run a sum over I. You have for that you have delta I is x. Let us give it value x, or let values of I be say, suppose value of j is x. We are in search of x component of this gradient of the tensor, x component. If j is x, keep that thing in mind. Now give different this value. You know values of I are x, y, z, and values of j are x, y, z. Take for example the value of value of j x. So you have now this I x e square. Now run a sum over this I. You have minus 1 by 2 del delta x e square plus delta this chronicle delta x. You gave a value x to I. Now value y to I, y less x. This j will remain constant. E square plus delta del z x e square. You know this term will vanish. Because in this term I, j are not equal. So this value will be 0, this value will be 0, this value will be 1. You are left with simply this minus 1 by 2 del e squared minus 1 by 2 del e squared. Having done this now, but just a minute, we have one more thing, that is this del. This del is basically, as you know, this del is basically minus 1 by 2 del I e square. We still have to sum. We have taken sum over this, but not sum over this. That's wrong. We have to take that as well. So we have to take this sum, and when we do it, it will yield us simply minus 1 by 2 as it is del x e square plus del y e square plus del z e square del x del y del x del y del z e square. And out of these only this term will survive. These two terms will vanish because the delta that you have here is delta. Here will be. You can take delta out because after all it's a number. You can take it out of this. So delta here will be xx. Here it will be xy. Yx rather. Here it will be zx 0 0, and you are left with only this term. And so finally the value is minus 1 by 2 del x, which is of course del x e square But what was x? What did we use x for? We used it for j. So we have 1 by 2 del j e square. Maybe this you might have been confused because of this. So let's repeat it in a minute. You have the situation this. You have delta ij e square. Delta ij and del square. First del square, then delta ij e square. But you know del square is delta I. That is, this is equal to del I square. It's not square here. Sorry, it's not square. Square is on this del I delta ij e square. And when we expand this, we write del x. We give value x to it. Delta x and j we have chosen as x e square, then delta y del y delta y, value of I is y, value of j is x e square plus del z delta z x e square. Now here delta xx, that is 1. Rest of these are 0 and 0. You are left with this, and then it is del x e square, because this is 1. Now what was x used for? It was used for j, so we got del j e square. Now hope that it is all clear to you. Going back to our this starting equation third, we have del dot t jth component equal to, we can write now easily this. We have now the value. We have, let's go back to this third. We have epsilon naught, okay, epsilon naught is there. Then del ei. Now see, you can see what we got. From this we got this and this. Value of this was this, but value of this I have not written here. It is you see it is e dot del ej, e dot del ej, and then value of this that we have determined, value of this value of this and this theorem we have determined. Now we can write this. Writing the value of this del dot t epsilon naught, then epsilon naught, and then you have this term that yielded us, this term yielded del dot ej minus e dot del ej. I think it is easy for us to remember. Del dot ej del dot ej del dot ej minus e dot del ej. Then we got, in place of that, minus 1 by 2 del j and e square. Okay. Then we have magnetic term. Exactly this we will get terms of this type. There we have, but with one difference, that is we have to write 1 by mu naught, then del dot b ej minus E dot del Ej and then we have minus 1 by 2 minus 1 by 2 del j and b squared. Now compare it with the expression for lowest expression for our this force per unit volume, electromagnetic force per unit volume, that was epsilon naught. I will write it first here. Epsilon naught E dot del dot E into E plus E dot del into E then 1 by mu naught plus 1 by mu naught, and then we had del dot B into bj into B and minus I'm sorry, I've written here this bj and minus 1 by 2 del j del b square. Obviously you can see, and then one more term, that is epsilon naught del by del t E cross B. Okay, it is quite clear now for you to see that this whole term, this whole expression from this to this, except for the last term, can be replaced by a very simple expression, that is del dot t, jth component of that. Of course, it can be replaced by that. We have then del dot t minus epsilon naught, and now this term. You see, as pointing vector is equal to 1 by mu naught E cross B. So value of E cross B in terms of pointing vector is equal to E cross B is equal to mu naught S. Substituting that there, you get mu naught S del S by del T. This expression is very, very important. It is also a Poynting equation, but written for force per unit volume, for electromagnetic force per unit volume. Now, what does this tell us? Let's see what it tells us. First of all, total force acting on electromagnetic force acting on the charge in the volume, given volume, that is equal to, we can take integral of say this volume integral del dot t d tau plus minus volume integral epsilon naught volume integral of epsilon naught mu naught del S by del T d tau. No, these volume integrals can be converted into surface. This volume integral can be converted into surface integral by using Gauss's theorem. We can write f is equal to converting this into surface integral. You need not now write divergence. You can write directly. Divergence will be changed into flux dA surface closed surface S, and then you have minus mu naught epsilon naught d by dt volume integral S del t. Under certain conditions, the second term on right hand side may vanish. For example, if we know that S is given by 1 by mu naught E cross B. E cross B. If E cross B vanishes, then S is 0. That is one choice. E cross B vanishes, S is 0. Okay. Maybe, for example, E cross B, these are parallel. Electric and magnetic fields are parallel. So S may vary, S will be 0, and then in that case this whole term vanishes. Another way is, if E and B are there and they are not parallel, they may be perpendicular, but they are not time varying. Now if they are not time varying, then d by dt of that, since you have rate of change involved here, the rate of change of that S will be 0, and then this term will vanish. Under these conditions, known as static conditions, under static conditions, F is equal to, we can write F is equal to TdA, okay, S. Now here, this equation provides us with physical meaning of T, Maxwell's stress tensor. And what this physical meaning is, you can see yourself now. It is T into area. This much, this term is force. This is force. Because this whole is equal to force, hence this must be force. You can integrate only forces to get force. Now T is equal to F by area. So T is force per unit area. Force per unit area across this surface S. This surface S. Electromagnetic force per unit area across this surface S. This is that is why the word stress, we call it Maxwell's stress tensor, because it's force per unit area, and force per unit area is stress. Now this stress can be either pressure stress, or it can be this shear stress. That depends upon what? The diagonal elements. If you have non-zero diagonal elements, each diagonal element stands for pressure, and non-diagonal elements, they stand for shear. That is the physical meaning of Maxwell's stress tensor. We'll talk more about this while discussing conservation of linear and angular momentum. Till then, thank you for being with me.